SQL stands for Structured Query Language. It's a language we use to communicate with relational databases. Relational database is the idea of storing data in tables that contain rows and columns. For example, if you think of Microsoft Excel, within Excel we have columns and we have rows. Tables are referred to as relations, columns are referred to as attributes, and each row is referred to as a record or tuple. Some popular relational databases you've probably heard of are Microsoft SQL Server, Oracle Database, MySQL, and Postgres. These are popular choices because relational databases help developers and database admins easily categorize and store data that can be queried for exact data sets. They're usually easy to set up, and new tables can be created without needing to modify existing applications. They also provide accurate data because it's stored only once, unless designed not to. SQL is flexible and dynamic, meaning tables and lots of data can be meshed together for one returning result, and has great security practices if they are utilized. This course is designed for beginners and those who have heard of SQL but just have not had the chance to get their hands dirty with it. Some of the takeaways I want you to have after going through this course is the ability to at least read from, write to, delete from, create and update rows, columns, and tables. We'll be using Postgres throughout this course as the database we'll run our SQL queries against. You'll find as you work in other databases, like the ones I've mentioned, don't exactly have the same types, built-in functions, errors, and other miscellaneous items. So everything that works within this course might not be 100% in other relational databases, but it will get you really close. Core commands like update, select, delete, and create are pretty universal between them. There are just a few subtle differences throughout each. After watching each lesson, be sure to check out the notes of the video. I'm posting links to various DB docs on the lesson topic so that you can dive more into them. I mentioned that this course is using Postgres for each lesson. If you're on a Mac, it can be easily installed through the Package Manager Homebrew. I'll link in the video notes how to install Homebrew if you don't have it. Once it's in there, all you need to do is go to your terminal and run brew install Postgres. If you're on Windows, download the interactive installer from the Postgres docs. This installer is pretty straightforward and will get you up and running quickly. You'll know that everything was installed correctly when you type psql postgres in your terminal and you connect to your local database. Let's create a table with SQL. Here we're going to be using the create statement. So we'll say create table users, and then in open parentheses we'll say create date. It's going to be a date. User handle is going to be a UUID. Last name will be a text, and first name will be a text as well. We'll close it off and then use a semicolon. Perfect. We've created our first table. The main principle to keep in mind here is the create statement. This tells your database that we'll be creating something new. We'll use the create statement to add other components within our database. So for this instance, we need to define what we're creating, which is a table. After we've established we're creating a table, we'll give it a name, users. Inside the parentheses, we'll define all of the columns within our new table and list the type of data that will live within this column. For example, the create date column holds date types of data. Each time data is inserted into this table, the data will need to match each data type or an error will be thrown. Text is referring to a string or a character type, and UUID is a universally unique identifier. Some other recognized types used in SQL are Boolean and ints for numbers. Each database such as Postgres and MySQL will have more granular and advanced types that can be used. I will link to some popular databases that use SQL below in the video notes. I recommend taking some time to go through these because they can vary greatly between databases. As you can imagine, when a table is created, it contains no data from the start. The first step in making our database useful is by adding data. We'll do this by using the insert command. So we'll say insert into users, open close parentheses, create date, user handle, last name, and first name. Values, we'll say 2018 June 6th. We'll paste in a UUID. We'll say Clark and Tyler. Close it off with a semicolon. Users is the name of the table we're inserting data into, and this first set of parentheses shows the columns that the data will match up with. One thing to take notice of is the order in which we define the columns. The data listed below in the second set of parentheses will insert according to the order these columns are defined in. When inserting data, there are two required components to work. First is the table the data is going into, and second is the actual data. We don't actually need to define the order of columns here. As we can see here, we did not provide the corresponding column names our data needs to match up with. This will insert into the table in the order the columns within the table were created by. It is generally accepted that listing your columns out is best practice because it's more explicit. Keep in mind that our desired inserted data needs to match up with the defined column types. For example, if we insert into our table with only two values, we're going to get a type issue because createDate is a type date and we're giving it a string of Jones. If we were to fix this problem, changing Jones to a date, we'd still get an error because now Debbie, the string, does not match up with a UUID type. We also don't need to provide predefined values. Most SQL databases have built-in functions that can generate values for us. So here we're inserting a new row into users with just the createDate column, and we're using a built-in function in Postgres called now. The now function returns a date type of today's date. And finally, we have the ability to insert more than one row of data at a time. All we need to do is comma separate new sets of data. So here we're inserting 3 new rows of data into our users table. Because we're only specifying createDate and passing the now to each set of data, it will provide null values for user handle, first name, and last name. Of course, if we wanted to add more data to each row, we just need to define the columns here and then provide the data here. You might be wondering if there's a way to bulk insert data into a table, for example, like from a CSV. The answer is yes, however, it's a little too advanced for this course. I recommend looking into that if you're curious. For Postgres, it involves the copy command. With data in our table, the quickest way to pull it all out is to write select star from users. And as you can see, we have 2 rows of data instead of our users table. One of the most common tasks when working with SQL databases is to query the data from the tables using this select statement. The select statement is very powerful and has lots of clauses and functions that can be used with it, but at a minimum, all that is needed is what columns we want to work with and from which table these columns exist on. The asterisk states that we want all of the columns within the defined table. We can also just select out specific columns by comma separating them. If we ask for a column that does not exist from our table, we're going to see an error. So if we ask for middle name from our users table, we'll see that the column middle name just doesn't exist in our table. However, SQL databases such as SQLite, MySQL, and Postgres have built-in functions. We can use one of these functions within the query, and our database will treat it as a column and input a value within each row. So even though current time is not a column within the user's table, it is a built-in function within Postgres, so it's handling it for us. We can also alias our columns within the query. If we add, say, first name as first name, last name as last name, and current time as just time, when we run this query, we'll see that we've changed the way our column names have rendered. This is critical to know when working with packages within languages like C#, and we need column names to match properties of classes. One common function you'll probably use a lot when working with SQL is the count function, which just simply returns the number of rows within our table. It doesn't matter if you use the star or just any combination of columns, as long as they exist within the table, it's going to give us a count of rows. And finally, we have the ability to do some filtering of data when pulling it out at the column level. Let's insert another set of data where the first name and last name matches data that already exists. So for first name and last name, we're going to insert Tyler Clark. So if we select out our data from our users table, we'll find that we have 2 rows that have the matching first name and last name of Tyler Clark. And if we use the built-in distinct function on the first name column of the users table, we'll see that we only get 2 rows back because it's removing the duplicate Tyler from the table. The same thing can be done for last name. And what's great is SQL gives us the ability to combine functions together, so we can get a count of all the distinct last names within our users table, which is 2, and compare that against just all the rows within our users table, which is 3. Our users table currently has 2 rows of data. a Tyler Clark, and a Debbie Jones that currently share the same user handle and create date. We want our user handles to be unique, which is why when we created this table, we gave this column a UUID type. So let's update my user handle to be a different value. Postgres has a handy extension we can bring in that will automatically generate a random UUID for us. I'll post links in the description on how to work with UUIDs in other databases. Now, with this extension created, we can update our user's table with a new user handle. When working with the update command, there are three pieces of data needed. First is the name of the table and column we're updating. Here we provide the table name and column name separated by this set word. Second is the new value that we want to update the row with. We'll do that by using the equal sign. And finally, which row to update. You might have noticed that we actually ended up updating both rows of data when we just wanted to update my user handle. While it did accomplish our goal of having unique user handles, if we're not careful, we could have shot ourselves in the foot by accidentally losing critical data. When working with SQL, commands like select, update, delete, these are looping commands, meaning unless a condition is passed, it will loop over each row of data. Ideally, what we should have done is add a where clause on our command that only updated the user handle for the row where the last name is Clark. We'll get more into filtering and the where clause in another video. For now, all you need to understand is that when updating, unless a condition is provided, like we did with last name equals Clark, it will apply to every single row in our table. And finally, we don't have to update one column at a time. We can update more than one column by simply comma separating them. By adding first name equals Danny, I'm updating both my user handle and my first name. Our users table currently has two rows of data, one for Danny Clark and a Debbie Jones. When we need to actually remove rows from our tables instead of just updating column data, we'll use the delete command. If we don't put a where clause with our statement here, it's going to loop over each row over our table and delete everything. So make sure before running the delete command on your table, you have a conditional clause that targets only the rows you want to delete. After defining which table we're removing rows from, we're saying delete all the rows where the last name column has a value of the text Clark. We're also able to add other combinations of conditions here within the where clause. For example, we could say where the last name is Clark and the first name is Danny, or even use the or statement here as well. The key point here is you want to make sure you're targeting the correct rows of data when deleting so that you don't actually lose the wrong rows. If you wanted to delete everything in our table, I mentioned you could just use the delete command without a condition. However, using truncate is a more performant way to do so. Unlike the delete command, it doesn't scan over the entire table. We also have the ability to truncate more than one table with just one statement by listing the other tables with commas. And finally, if we're trying to remove the table completely from our database, we use the drop command. Once we run this command, all of the data is deleted and we cannot query anything from this table. One of relational databases' best strengths is the ability to flatten data across many tables. They can be independent from each other, or we can connect them together. Adding constraints to tables is how we can connect them together and make sure our data keeps its integrity, and as we scale, it does so efficiently. Now let's create the users table. We'll give it a create date of date, a user handle of a UUID, last name of text, first name of text, and then we're going to do constraint pk users, primary key, and then user handle here. A primary key is a column or a group of columns used to identify a row uniquely in a table. It can be created by defining it as a constraint, as we did here, or since we only used one column as the key, we could have written it before the closing comma of this line for user handle by writing the words primary key. A table can only have one primary key, and whatever is defined here, the value inserted into the column or columns needs to be not null and unique. So what we're saying here is that this table cannot have more than one distinct user handle in it, or we'll get an error. As you can see, this helps keep our data in check because two users in our table with the same user handle could cause us some row issues down the road. And the pk_users is the name of the key we're giving it. You don't have to give it a name. Postgres and most databases will automatically create a name for you if you don't give it one. As I mentioned before, we cannot insert a null value in a primary key. It's recommended to always give your table a primary key whenever you create a new table. Now, if you wanted to make sure your users give you an email when they're signing up, but you don't want the email as part of your primary key, you can use the not null constraint. And while we're at it, we probably also want to make sure we always have a create date and a first name as well. So after dropping our users table, let's recreate it, but we're going to add this not null statement at the end of the columns we care about not being null. So that's going to be create date, user handle, and first name. With these constraints in place, we can now rest easy at night knowing that our data in our tables is a little bit more secure. Also, my own personal opinion is to avoid dealing with nulls in databases as much as possible. They can cause problems without you even knowing. Similar to the primary key constraint, the unique constraint makes sure that values stored in a column or a group of columns are unique across rows in a table. And as you can see, we can combine some constraints together, giving us the flexibility to make sure we keep our data in a maintainable state. Let's wrap up by recreating our user's table and the desired output. Create date is not null, the user handle is unique and not null as our primary key. Users can have a null for a last name, and our first name is not null as well. We want to start tracking all the purchases our users make, so we'll create a purchases table. But we want our data between the two tables to be true, meaning we should never have users make purchases that are not in our users table. How difficult would it be to find that people are making purchases and we don't have their data in our users table? We can do that by creating a foreign key between the two tables. By adding this references constraint here, we're adding a foreign key that states whatever value is inserted here within purchases, it needs to exist on the users table as well. With that in place, if we try to insert a random user handle into purchases, we get an error. It tells us that we're violating our foreign key constraint. And if you're curious, you can add constraints to already created tables through the alter table statement. Imagine going to math class at school and you're given a book that put all of the topics such as geometry and algebra in an unorganized manner. Everything was spread out and jumping between topic and topic as you read through the book. Chapters within your math book and any book help organize the information and can put similar groups of topics together so that it's easy to navigate and learn. Similar to chapters in our math books, when we insert data into our tables, we can tell our tables how to organize this data. Adding what's called an index to our tables is one of the best forms of database performance you can do. An index allows the database to go to predefined chapters, if you will, that we can define for it. Our users table currently has 3 rows of data. When we query from this table, let's say that we almost exclusively just care about individual user handles. We can create an index on this table by saying create index test1 user handle index. On the users table, we'll say user handle here. Perfect. Let's look at this statement again. The create command does exactly as it seems. It's creating an index. And then this part is the name of what we're calling it. It can be whatever you want, but you might want to try to make it something meaningful for your personal work. Next, we define the table this index will live on and what sets of columns we want to organize our data by. We could pass through any number of columns here. We can also create another index on the same table that organizes data behind the scenes by create date and user handle. This would be great if we constantly queried out from this table where user handle equals blank and create date was between certain dates. Each database has its own way of showing what indexes are on a table. In Postgres, we just type \d and the table name, and here we can see the 2 indexes that we've created. To remove an index, we simply use the drop command with the name of the index we've created. And that's all that's needed to remove an index. At first glance, you might be thinking, why not create many indexes on a table? Although indexes are designed to enhance a database's performance, there are times when you should avoid them. For example, don't use indexes on small tables, tables that have frequent large batch updates or insert operations, and where columns are frequently manipulated. If you think back to our math book example, imagine now a very large math book that constantly had topics added to and removed from. Without organizing them in chapters, it's quick and easy to just add the info to the end of the book. However, with chapters, with each insert, we need to scan all of the indexes and make sure we put the right data in the right location. This creates a lot of overhead and can actually cause you more problems than it helps. Now, we could spend hours talking about indexes. There are a lot of different types, such as partial, implicit, and unique indexes. However, this is a basic and the most common example of using them. If you're interested, I'll be posting links in the video's notes for more information. Our users table currently has 4 rows of data. We've got a Tyler, Debbie, Mary, and Patrick. They each have unique user handles, but 2 of them share the same create date, 2019, January 10th, and then one has one in 2018, and the other one is February 1st of 2019. When we select out data, I want to be able to group common column values together. For instance, I want to get a count of shared create dates. The group by clause does exactly what you would assume. It combines the rows returned from the select statement into groups. So this is telling us that there are 3 groups of rows. Even though there are 4 rows in our users table, since we're grouping by create date and 2 rows share the same value, we get 3 groups. Just to show both sides, when none of the rows share, let's say, a user handle, we'll get those 4 rows. Just seeing the count isn't really helpful because we don't know which create dates are actually shared. So let's pull that out as well inside of our select statement. Now we know that the January 10th date is the one that has 2 rows grouped together. Let's also pull out the first name column values as well. As you can see, we're getting an error. This is telling us that the first name column needs to be added to the group by in order to pull this out. Remember, our rows are being grouped together by create date. Because more than one row can be in a group, as in our January 10th example, our database doesn't know which first name value to pull out of the grouping, which is why we're getting this error. If we add first name to the group by, we no longer get this error, but instead get all 4 rows back. This is because our group by is now looking to create groups that share create date and first name. Because none of our rows share these 2 columns, we get all 4 rows out. Keeping this mentality of grouping in mind, most SQL databases have built-in aggregate functions. For example, if we wanted to find what the lowest value create date was within our table, we'd use the min function. Aggregate functions are closely related to grouping operations like group by, which is why we'll get the same errors we did before when trying to pull out our first name column with the min function. As a side note, if you're curious on how to accomplish the tasks I've talked about in this lesson, I'll post those 2 queries in the notes of this video. We need to do a little bit more than just group by and aggregate the create date values. Some other common aggregate functions are max, which does the opposite of min. There's sum, which sums up values, and average. Be sure to check the notes of this video for links to popular SQL databases that implement these as well as their own functions. When we use the select statement as is, we get everything out of our table. If we wanted to filter the results down to specific rows, we use the where clause. So within our select statement, let's say select out all the columns where the last name equals Clark. You can think of the select statement as a for loop. We're looping over each row within the table and pulling it out. This where clause is how we can filter down what actually gets returned. Only having one condition within our where clause did the job. However, we could get more specific and add more cases. We can add on to our where clause an and first name equals Tyler to get the same row back. Using the and logical operator means that both cases provided here have to be true for any rows to be returned. We could instead use the or logical operator as well, which means that at least one of the 2 cases needs to be true. And then when working with dates and numbers, we can use other operators such as the greater than. So say, give us all the rows where the create date is greater than May 5th, 2018, which is going to be both rows. We can use the less than, which will give us neither of the 2 rows, as well as equal, which again will give us neither. There is greater than or equal, which will give us back our 2 rows because they're greater than May 5th. There's the less than or equal, which is none. And finally, the not equal, which is going to give us our rows because both rows have a create date that's not equal to May 5th. There are a couple other special operators as well. I'm going to insert a row into our table that has a null last name and first name, as well as a different create date value. With this in there, we can say select out the rows where the first name is null, and this is going to give us that 1 row. When working with null values which signify unknown, we cannot use the equal sign because it will return null itself, not a true or false value. So we have to use this is operator. Another fun operator is between. So we'll say select from users where create date between 2018 May 1st and 2018 September 1st. This is going to give us all three rows because the create date falls between this range. We can exclude the August date by changing the last range to in July 1st. And finally, there is the in operator, which gives us all the rows where the last name column equals any of the values within this list. The list is separated by commas, and we can work with strings or numbers within these parentheses. As we see here, we did not get that third row, which had no values for the last name and first name columns. If this is the first time getting your hands dirty with SQL and databases, you might find yourself thinking that your tables need to hold as many columns that are relevant as possible. For example, when dealing with users, as in our case, we could add more columns for email, address, phone number for each person, and then gone even deeper with their user history, like if they've changed their email from what to what, and then a column for when that happened. Before long, you'll find that your table has too many columns to keep track of, and eventually this one table will have to deal with a lot of transactions at the same time, especially as you scale your application. So instead, we want to keep our tables simple and modular. We have our users table with 3 users. I've also gone ahead and created a purchases table that has 2 rows of data. Each one of these rows represents a purchase that someone from our users table made. Now let's say that we were making a dashboard within our application that displayed the user's information as well as their purchase history, which is really common. We could make 2 separate calls to our database to get this info, one to get all the info about the user and the other to get all of their purchases. Instead, what we can do is get it all out in one query by joining these 2 tables together. In our first example, we'll use the left outer join. Now let's walk through what's happening here. We still use the select star, which will pull out all of our columns returned from the rest of our query. We say from our users table, and this U is aliasing the users table, kind of like making it a variable that we can reference throughout the rest of this query. We then say left outer join with the purchases table, aliased as P, on the matching user handles between the 2 tables. Now let's get more into the join. If we zoom out enough, you'll see that we now have our 2 tables columns added together to form one large table. All of the users' columns are accounted for, as well as purchases. You can see we have 2 user handle columns because they're both shared. When joining tables together, we tell it what condition to join on. This is why we need the on statement in our query, so our tables know where to fuse. You'll notice that Debbie does not have any purchases, so all of the columns are holding the null value for each of her purchase columns. Left outer join is saying get the table and all of its rows stated to the left of the join statement, in our case users, as our starting set of data. With this data, match it up with the following purchases table rows, filling in null values for any missing rows, which again is why Debbie's purchase columns has null values because she doesn't have a row in purchases. Now let's change our left outer join to be a right outer join, and we'll see what we get. We have to zoom way out to see everything. And now with our right outer join, we're not starting with a user's dataset first. We take the right table's data, in our case, the 2 purchases table rows, and match up the user's rows with them. So we start with 2 rows, and that's what we end up with in the end. As you can see, Debbie doesn't show up in this list because she's not in the purchases table. Now let's insert a row into our purchases table and have it generate a random user handle that does not exist in our users table. We'll rerun our join statement and see that because there's no matching user handle for this newly inserted row that matches our users table, we fill in null values for the users table data columns. Now what if we want both missing rows of data in our combined ultimate table? So we want to see Debbie in here as well as this purchases row that does not have a matching user. We do that by using the full outer join statement. The result is we have 4 total rows with null values inserted for missing columns on both sides. Now there's also inner join, which is the opposite of full outer join. It only returns an ultimate join table where there's a matching user handle on both tables. And finally, there's cross join, which doesn't take a join on statement because it takes the first table's rows and assigns it each row of the joining purchases table. So as you can see, I'm in here 3 times because the purchases table has 3 rows of data. So my users row is duplicated and matched up with each row in purchases, which is why cross-join doesn't accept any on conditions. There are a couple final points to know when working with joins. If we specifically ask for a column that is shared between two joining tables, we'll get an error asking us which column from which table to pull out. This is why we need to alias our tables so that we can specify which table-column combination we want to pull out. Another tidbit is we only had one join on clause. You can add more conditions by using AND. One of my personal favorite aspects of SQL is the ability to write queries within a query. This composability makes it easy to pull out intended data all in one call, rather than making multiple calls and getting data out in pieces. In the grouping and aggregate lesson within this course, we wanted to pull out the row that had the earliest create date. If we do min on the create date and then pull out the first name, we get an error. Our database doesn't know how to handle the other columns while it's aggregating all the create date columns down to 1. If we add first name to the group by, we see we get all 3 rows out, because now that first name is grouped by unique first names, we'll get out the min per grouping of first names. Instead, what we want to do is use a subquery. For that, we'll write select create date and first name from users. We'll use a where create date equals a subquery selecting out the min create date from our users table. You see that this returns my name for first name and my create date. In order to use a subquery, it needs to be wrapped in parentheses. Our subquery here returns one min create date from our users table, and that's what we use to filter by, where our min from the inner query matches the create date from the outer query. With this filter matching on the correct row, we can just pull out all the columns then. Subqueries can be used in other commands such as insert, update, and delete. Let's update the first name column of the row that has the earliest create date to Danny. Here you'll see that we've changed from Tyler to Danny. So not only can subqueries be used as a way to filter, but we can use them as a table to join on. So let's write select total and first name from users, US, inner join on a subquery. We'll do select count of user handles as total, user handle from purchases. We'll group by user handle, close parentheses, and then we'll say where user handles match. With this in place, we'll see that Danny had 1 purchase and Mary had 2 purchases from the purchases table. Let's walk through this again. The top level query is going to give us one column that exists on users and the other that we create from our subquery. Our subquery is getting a count of grouped by user handles. This count tells us how many rows are in each grouped user handle. We inner join on the user handle we pull out from the subquery and the user handles that already exist on the users table. The returning results show us how many orders each person purchased. Another option is using subqueries as a column value. For example, I want to return the average order size along with all of my SKUs and user handles inside of my purchases table. I can add a subquery next to my other columns. When I run this, you'll see that I get all of my user handles, all of my SKUs, and a consistent average across all of the quantities within the purchases table. To clarify, this isn't stating that the average for this user for this SKU is this value. This is just the average quantity for all of the purchases made inside of our purchases table. I will, though, post the solution for making this average be a reflection of this user handle and this SKU in the notes. But before you look, see if you can do it yourself. You'll want to insert another row with the same user handle and SKU and a different quantity to make sure it's working like it should.